This video is going to primarily focus on box plots, otherwise known as box and whisker plots. Previously, we looked at histograms of the area of fires. Uh, for the box plot, we're not going to do that, really just because the box plot would be so squished it would be nearly impossible to interpret. And we can tell that by looking at the data, and I've taken the area of fires here and I've sorted it to make it clear. At the bottom of the scale, we have a minimum fire area of 10, and then we're in the hundreds, and we stay in the thousands for a while. And the far end, we have 12.6 million and 5.8 million square meters. These are very, very different values from what most of the data are. I think it is fair to say that they are outliers. Probably not wrong, but definitely outliers. They don't follow the pattern of the data. And because of that, if we were to do a box plot, our plot would have to range from 10 to 12.6 million. I've actually color-coded some of the important percentiles here, the 25th, 50th, and 75th percentiles. And we can see that those bottom percentiles are in the low thousands. So again, trying to draw this plot to be able to see these clearly when the upper limit is 12.6 million isn't going to happen. So in real life, we would probably want to and need to find some other way of visualizing this. Honestly, we'd do some sort of data transformation, which we did not talk about in class at all. So for this presentation, we're going to focus on the number of fires instead, and that will plot much more cleanly for us. Before doing that, I will take the moment to say that this area of fires in the presence of these extremely high values in the data is a great example of when we might want to summarize our data, the central tendency and the dispersion, using the median and the median absolute deviation, and to use those guys instead of the mean and the standard deviation. Remember that the mean and standard deviation is very sensitive to especially very high values or very low values, values that are very different than the rest of the data. So the mean and the standard deviation would be driven by the 12.6 million and the 5.8 million values in there. And we probably would not want that. Those two are not representative of most of the data, but they would drive the mean and the standard deviation. In contrast, the median and the median absolute deviation would not care that this is 12.6. It would just care that this is the highest value. So they are considered much more robust, more immune to outliers. Okay, box and whisker plots. Let's do some drawing. Unfortunately, before we do some drawing, we have to do some calculating. And these are the different components of a box and whisker plot that you need to calculate before you can get to drawing one. The first thing you have to calculate is the mean, or first thing you have to identify. So I've taken our data set. It is no longer sorted because it's sorted by areas of fire. So let's sort this. We can see that the minimum of the data are the number 1, and it doesn't matter that 1 appeared in multiple places. The minimum is still 1, so that goes here. We'll skip this part for the moment and look at the 25th percentile. Here I've used a built-in Excel function to calculate the value for me. In class, I don't think we talked about the function. We did it more manually, which was like this. We take the percentile in decimal form, and we multiply that times the number of data. So here I use the count function. There are, in fact, 17 data points, so it would be fair to just to do 0.25 times 17. And that tells us that the median is data point number 4.25. So the 25th percentile is not 4. That's not the value of the data point. This is the index. It is the location of where the 25th percentile is. So it says that the location, the index, is data point number 4.25. So here's data point number 1, 2, 3, 4, and then we need the next one because our median is greater than data point number 4. So it tells us that our median is this particular row, and the value in this row is number 1. So the 25th percentile for us is still 1. We'll take the same approach for the 50th percentile. There's the Excel function. .inc means inclusive. So Excel will calculate that for us. If we were to do it by hand, we can take 0.5, the percentile that we want in decimal form, multiply that times the number of data, and that tells us that the 50th percentile is data point number 8.5. Again, this is the 50th percentile is not 8.5. This is just the index, the location of the data. So this is data point number 1, 2, 3, 4, 5, 6, 7, 8. And then the next one, since we're greater than 8, means the 50th percentile has a value of 2. Data point number 8.5 or data point number 9 has a value of 2, so that's what we get. One more time, 75th percentile, there's our Excel function, and by hand it would be 0.75 times again the number of data, and that tells us the 75th percentile as data point number 12.75, data point number 13. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 tells us the 75th percentile has a value of 7. And that is also what Excel tells us it is. So excellent, go us. So there's 4 parts of the table. We need one more for now, which is the maximum. We sorted our data, so we can quickly pick off the maximum. We could also use an Excel function such as the max. I don't think I showed it, but the minimum has a very similar function. And we have to do another calculation to calculate the IQR. This is the interquartile range. So the inter means really between or within. Quartile means we take a thing, we divide it up into 4 parts, like quarters, and a range is the difference between the two. So it's not an interval. We don't get 2 numbers like a confidence interval. It is the range. It is a single number, which is one number minus another number. So here we want to take the number that we calculated for the 75th percentile and subtract from it the 25th percentile. So 7 minus 1 is 6. And that is the interquartile range. It is the middle 50% of the data. 75% minus 25% is 50%. And the range of that is 6. Having calculated the interquartile range and our other percentiles, we do 2 last calculations. The first, and these are for possible whisker locations. First, we take the 25th percentile and we subtract 1.5 times the interquartile range of 6. So our 25th percentile was 1 minus 1.5 times 6 gives us minus 8. And we do the same kind of thing, but opposite. We take the 75th percentile and we add 1.5 times the interquartile range. And so that's our 7 plus 1.5 times 6 gives us 16. Now when it comes time to do our box plot, we may not use all of these. Generally we will compare the minimum and this potential bottom whisker, and we will use one of those as the whisker. And if we have other data outside of that, they will appear as dots. And similarly, we will compare the maximum of the data to this potential whisker, and we will use one of those two as our upper whisker. And if data extend past that, then they will appear as dots. Hopefully that'll be a little more clear when we actually draw this out. So let's get drawing. Generally easiest to start with the fixed percentiles. I tend to start at the 25th percentile, but it doesn't particularly matter. The 25th percentile is at the number 1, so we will draw a line here at 1. The 50th percentile is at a value of 2, so we will draw a line at the value of 2. And imagine this, the 75th percentile is at 7, so we will draw another line at 7. So these 3 percentiles all get connected together as a box. Sometimes that middle one has a different color. Sometimes it's represented as a dot or an asterisk. I don't particularly care how it works, as long as it's on the plot there and clear what it is. We then need to draw the whiskers. So the minimum whisker will be kind of down here to somewhere. The minimum whisker will extend down to whichever one of these is closest to the median. The other way of saying that is it will extend to whichever one of these is larger Now 1 is larger, it's closer to the median than -8, so our whisker is going to extend down to the value of 1. Well, we already have a line at the value of 1, so we don't actually have a whisker in this plot. The minimum of the data is the same as the 25th percentile, so this one does not get a whisker. It wouldn't really make sense to put a whisker down to a value of -8 because we have no data that far. The lowest data point we have is a 1, so we wouldn't want to extend our plot to anything past the lowest data value, so we won't end up using this one at all. We're going to follow a very similar idea with the upper whisker, which will extend up here to some value, and we extend it to a height of either the maximum or this, depending on which one is, again, closer to the median. So for the lower whisker, we stopped at whichever was closest to the median, kind of the largest of these. And here we're going to, again, extend it to whichever one of these is closest to the median, which will be the lower of these. Now 10 is smaller than 16, so we will extend our whisker up to the lower of these, or up to whichever one is closer to the median. Same thing, which for us is a value of 10. So we will draw a line here, and this is a whisker format, so it looks something kind of like that. Similarly, even though we had a value that was at 16, our data does not extend past a value of 10, so it really wouldn't make sense to have anything in our plot that goes beyond the range of our data. That really just would not make sense. So in this case, the whisker stops at 10 and we don't have anything else. That is our box plot, our box and whisker plot for this data set. I would like to add one thing kind of by hand just for demonstration purposes. And that is if we had one more year, let's pretend we had a year, and that last data point was at 14. So we're just kind of making this up. That means our maximum here is now 14. And so what would that look like? Well, in this case, 14 is still less than 16. So we would move that, and we'd have a new line at 14. And it would still stay something like this. So let's add another data point, that is 17. So our new maximum over here is no longer 14, it is now 17. So now when we compare these, we have 17, which is now greater than 16. So our whisker needs to stop at whichever one of these is closest to the median, so whichever one of these is smaller. So the whisker is not there anymore. The whisker gets drawn at the smaller one of these, which is at 16. So now it's way over there. So there's our whisker, but we still have a data point that is not represented in this graph. So any remaining data that are greater than the whisker, and same thing if we had data that was less than our bottom whisker, any of those data points are represented with a dot. So we have one data point at 17, so we would draw that data point up here as a dot for 17, which is greater than our whisker. So that is how that works. I think the last thing I'd like to do is do just a quick comparison on what this box plot would look like as a histogram. So we had a problem set question that asked you to do this formally. I'm not going to have you do that formally, or at least I'm not going to demonstrate that here. It's really in reality, when it comes time to make plots, we do things out of frequency tables. We would not take a box plot and directly make a histogram from that. We would have a frequency table, and we would make a box plot, and we would have the same frequency table, and we'd make a histogram from it. It is important to be able to look at something like this and know really, is it skewed, and what direction is the skew? So hopefully it's kind of evident that yes, this is skewed. Our median is not in the middle, and if our data were symmetrical, the median, the 50th percentile, should be in the middle, and it's not. It's over here. And we also have this huge whisker, and that huge whisker does not appear on this side of equal length. Again, saying, well, our box and whisker plot is not symmetrical, so our histogram is also not going to be symmetrical. So what would this particular plot look like? Perhaps the easiest way of thinking about it is the whisker is the equivalent of a tail. So we have one tail that's up here in our kind of more positive values. So if we were to plot a histogram just by eye without worrying what the left-hand side was doing, we know we're going to have a tail off to the right, and this one will do something kind of like that. There's some uncertainty as to whether or not this is going to go down or maybe it just stays across. Really, the important thing is to know that most of our values are going to be here on the lower side, and then we're going to have this right-hand tail that matches this long positive whisker. So positive tail, positive whisker. And that's it.